So we are very happy to have Professor Rob de Boer here. Professor Rob de Boer is a professor of theoretical ecology at Utrecht University, and also external faculty fellow at the Santa Fe Institute. And he will talk about, I think his main interest is theoretical immunology, but he's talk about how herd immunity mitigated a deadly second wave of COVID-19, and also some connections to immunology, I guess, to them. Okay, the floor is yours.
Yes, thank you. Thank you for the invitation. Nice to give a talk here. So indeed, my main interest is in the immune system. We also do all sorts of things in the immune system, trying to characterize the population dynamics there, but also studying things like the immune system as a complex system. Every day it makes choices. Should I respond to this bug? Then should I make antibodies, or should I make another response? If I eat something strange, should I respond to this? So the immune system makes also decisions, and the immune system has memory. If you have seen a virus, you remember that for a long time. So the immune system by itself is a very interesting distributed complex system, and I often talk about this, but not today. And I decided to talk about a recent project that we did with a student, Jan-Paul Vermenen, and an epidemiologist, Michiel van Boven. And we were helped by Chris van Dorp, who was a previous PhD student from me, who worked with the program. And the story is about the corona pandemic in Manaus, the city in Brazil. And it's not all epidemiology. At the end, I will have a nice immunological method, and that is what that's my major message that I would like to get across. I was warned that the talks are interactive here, that you interrupt me with questions. I love that. I don't have too many slides, so ask as many questions as you like. In the end, we somehow will get to the end, and I'm really not worried about that, so please interrupt me. Okay, and I have a few introduction slides before we get started. So first, Manaus is a big city in the northern part of Brazil, in the Amazon area. It's about 2 million people. It's a poor city. Many people have to go to work every day. There was this pandemic going on there. There were no lockdowns. The people just had to go to work. The children just went to schools. That led to an enormous epidemic. And probably you all remember these pictures from the newspapers that they had to dig mass graves because there were so many extra deaths every day. And that the cemeteries and graveyards would no longer support this. So here, on the, how do we do with this pointing? Maybe I should stand here. Here on the right, you see March 2020, and there was this peak in the number of people dying per day. And you see that amounts to about, I should even say the excess people dying per day. And there's two measures here, the excess deaths that are being reported by the graveyards and the cemeteries. But there is also hospital deaths, I will call them SARI, acute severe respiratory infection. So people dying in the hospital being diagnosed with some severe respiratory infection. And that will at that time almost 100% be corona. And this data is just online. That's it's amazing that this is all available, but for every day in this period, we know how many people in the hospitals died from corona. At the peak, there was about 150 people excess deaths. And at the end of this epidemic wave, about 70% of the people had antibodies to corona in their blood. So 70% of the people had seen the virus. So the whole world hoped that this was the first case of herd immunity. This was a city where almost everybody has seen the virus. So hopefully these people were immune. So it was extremely disappointing that at the end of the year there was a second wave, and the number of deaths in the second wave were almost twofold higher than the number of deaths in the first wave. So 2/3 of the people dying from corona in Manaus were dying during the second wave. And the first wave was due to a particular strain of corona, and the second wave was due to another strain of corona. The virus evolves, it evolves escape mutations such that the antibodies no longer work. And this gamma P1 strain sort of dominated in the Southern America. Here in Europe, in the Western world, we had some other strains, but basically we had similar pictures. From an epidemiological point of view, this is sort of unexpected. If you have a population that is for 70% have seen the virus, then most of these people will have some sort of immunity to this virus. And if you then get a new variant of this, of the same virus, you expect some immune protection, so you expect a smaller wave, and you expect fewer deaths. So it was very surprising and very unfortunate that this second wave was so severe. And I heard this is a very general, so let's just go through this. I'm going to do a one-slide introduction into the standard models in epidemiology. Probably you all know, but then we just waste a few minutes. So the standard models in immunology are called susceptible, immune, recovered. So you have a susceptible population, people get infected with some disease, they are infected for a while, and after a while they recover. But if the immunity is not long-lasting, then recovered people may go back to the susceptible state. That's here. From the recovered, you go back to S, and then you have an SIRS model. And you can define a rate at which immunity wanes, and I will call that W here. Let's very quickly look at the equation. So you have susceptibles, they get infected. The typical parameter that you use is beta. We use many betas today, so I'm explicitly beta. Susceptibles get infected if they meet an infected individual. Infected individuals, they can either die or recover. The recovered guys end up in the recovered class, and from the recovered class, you can go back to susceptible. If you run a model like this, that's shown here, you start with all susceptibles, you get your epidemic, the susceptibles go to the recovered state, and then you end with a steady state in which the population is immune to this virus. The number of susceptibles here at the end is so low that the infection cannot come back. The infection depletes the number of susceptibles to the level that its fitness or its R0 fitness becomes 0, that R0 becomes 1. Please.
Where because there is death of the infected individual.
In this case, there is no death of the infected individual.
So this is
Sorry?
the one. There are three curves. So the blue one is the immune people.
This is the blue one is the recovered,
Recovered.
green is susceptible, and red is the infected. And the immune people would be the recovered. And indeed, as André is pointing out, in this simple case, there is no death.
Tap twice, if you tap twice the thing, then it comes back to full screen.
The idea is you always have some susceptible people because you don't never get 100% immunity like the whole population.
No, because the epidemic dies out at some point. There are not enough susceptibles, so the virus is trying to replicate, but at some point, the number of susceptibles is too low for the virus to further replicate. So the end state is always a state at which there are some susceptibles left. But the number of susceptibles that are left are sort of the steady state of the system. The infection cannot come back. Okay, this is an epidemiological model for one strain. We have to talk about two strains today. So what is the standard way to do two strains? You have your S, and then I call it I1, infected with the first strain, R1, recovered from the first strain, and then either you go way back to susceptible, and you can get infected with rate beta 2 with the second strain, and you become an infected individual with the second strain, and then you can recover to a recovered individual of the second strain. And those can wane back to susceptible again. But you can also make these models where you say, if I have a recovered individual from the first strain, there's only partial immunity to the next strain. So with some other beta 2 prime, recovered individuals can be infected with the second strain. And then beta 2 prime should be smaller than beta 2, because these people will have partial immunity. Yeah, so then I can make a 2-strain SIRS model. Is this clear to everybody? Good. We thought we needed to do better, and I will also show that that helps. So here's the same scheme as I had on the previous slide. And now we change that into the scheme that is depicted here. And what do? We say from recovered, you indeed wane, but you don't wane back to susceptible. You wane back to a new class of people that are maybe partially protected or have some other properties. So we define a class of W1, people who waned from the first infection. They don't have antibodies anymore to fully protect them, but they're also not fully susceptible. And then a waned individual can be reinfected with the second strain, that's the beta 2 prime, and become a reinfected individual with the second strain, an I prime 2. And these two blue categories, they can have different properties than the wanes and the I2s in the previous model. And obviously, if you have susceptible people left, there will be a primary infection rate that we still call beta 2, that you go directly from susceptible to infected with the second strain. And then individuals that are infected with the second strain, they can recover and they can wane again. And then you would have individuals category W2.
Why do you distinguish I2 and I2 prime?
That will be
different recovery rates.
They may have different recovery rates. They may have different death rates.
Okay.
They have some pre-existing immunity. That will later. That will be essential. These guys, the infection by the second strain is sort of at the same level, but the death rate is much lower. There was another question. Yeah.
So people get infected by the second strain first. So the beta 2 sort of pathway.
Yeah, that is.
So does that also affect their, because I assume if they get affected with the second strain, like after that and recover from that, they can still get infected with the first strain as well. Does that
True,
also affect
true.
the probability of being infected by the first strain?
Yeah, but let's go back. So the B195 strain sort of went extinct here. It was replaced by other strains. There's a few other strains that never became dominant here. And then this gamma P1 strain was not present early on. It really evolved from that strain. So indeed, there's a time issue here. You have in the beginning just the one strain, then there is a sort of period where you have strains that we don't model, and then you have a second strain, and the two strains don't coexist. Yeah.
So you replace this because in the first scheme you have waning and you go back to susceptible, but you can also be reinfected.
Yeah.
You go from R1 to I2.
Yeah.
These two processes you now merge into one waning process, right?
Yes. Well,
because you cannot
yeah.
go from R1 to being infected anymore.
Yeah, only via waning.
Only via waning.
Yeah, and you never go back to fully susceptible.
No.
Being
No,
infected once also that's some
Yeah.
history.
No, really, but
Yeah.
it's a qualitatively different
Yeah.
type of scenario that you're modeling. Yeah.
Yeah, and this, by the way, this new model has the same number of parameters as the second model. It's
Sure, yeah.
easy for us later if we want to compare the models. Yeah.
In this model, it's any death.
Yeah, I'm not depicting death, but indeed there is death at every infected stage. So there is a D1, a D2, and a D2 prime. 3 different death rates.
And did you make any change in the modeling of the deaths?
Yes, that will come later. Yeah.
Okay.
Yeah.
Because that would
Yeah.
be. Yeah, then I hold my question.
Well, will be fitting these rates, so the model can choose to make them equal or not. But they will be very different in the end.
Yeah, because okay, I'm Brazilian.
Yes, good, because that was my next question.
Yeah. So I follow only the news and never follow a model.
Yeah.
But there was expectation of herd immunity. And
Yeah.
also everyone knows the Brazilian government denied COVID.
Yeah.
And because there was this expectation, there was no supplies of oxygen. And then the second big spike was justified because people really died out of oxygen. It was not that necessarily there was increase in death rate, it's just people died lack of air. Was really sad, but sorry
Yeah.
to. And then I wanted for the modeling.
Yeah, well,
why this
maybe
encoded again.
then I have some interesting questions for you at the end. Yeah,
Yeah.
that's good.
So is there an immunological reason why you changed the scenario? So because
Yeah.
now you assume that there is full cross immunity for when you're infected with R1, but that it actually wanes over time.
Yeah.
And so is there any
Yeah.
immunological?
Yeah, so we're saying once you are in the recovered state, you just recovered from this infection, then there is really a period in which you are immune to all strains, you could say. You have high antibody levels, and they slowly go down,
Yeah.
and at some point you become susceptible again to maybe the same strain even, but in this case the same strain is gone,
Yeah.
but definitely other strains.
But like the question for the model is, for the second wave, is there any parameter that would include that there was no oxygen for everyone?
Yes, that would be the death rate of these two classes.
Which should be
But-
bigger. Or-
I will conclude, and that's why I say I have questions for you at the end.
Yeah.
I will conclude that the second strain was more deadly than the first one, but maybe you tell me the care of the people during the second wave was less good than the care of the people in that, and that is something that I cannot distinguish.
In Iran was really the second strain was more deadly when there was the Delta.
Yeah.
Variant.
Yeah, but for the news at least, I don't know, the first paper that I saw about this was really, there was no oxygen in the hospital.
Yeah,
So
yeah.
no one could be intubated anyway.
Yeah, but it was also not present in the first wave.
Yeah, but then,
Yeah.
but
Yeah.
we know a bit less than in the second wave.
Yeah.
Right.
Yeah, please,
Question.
please.
It seems reasonable from the data or maybe from where we studied theory that you can assume beta 1 and beta 2 are independent event. If they are random but independent event, is this interesting to consider if these two events are not completely uncorrelated? So they are random, like if you have two disease co-spreading, maybe they don't happen in such a way that you can decompose into two different channels like here.
Yeah, well, I'm not completely getting the question, but I can get it halfway. Remember that the two strains don't coexist. So
Because they don't
yeah, so the
coexist.
beta 1 events happen when the second strain is not there yet.
But if they coexist, then there can be some correlation, right?
Definitely. Well, you could also argue that, remember that after the end of the first wave, we have only 30% susceptibles left because 70% of the people saw the disease. For a second strain to invade into a population, there's only 30% susceptibles left. It needs a much higher infection rate because there are fewer susceptibles to infect. So if you do this with, if you model this with this model, then the infection rate of the second wave has to be higher. Beta 2 has to be higher than beta 1 because the population has herd immunity to the first strain at the end. Yes, please.
There's one thing I'm missing a bit here is it looks like you have one, it should be like one first model with a stationary state and then the second model come on top of the stationary state of the
So,
first model.
yes,
It's
yeah.
here, it looks like they are both happening at the same time.
yeah,
But it's-
that is true. So that's why we sort of put the second strain on the right-hand side of the cartoon. There is also some sort of time axis here, which is not displayed. Yeah, yes. Yes, good. Thank you for all the questions. This is going very well. Okay, so my next question is there somebody from Brazil in the room? And then I will say, Brazil is a beautiful country. And I guess you agree with me.
Yeah.
And it's not only a beautiful country in the general way, but it's really amazing what kind of data is made publicly available. We already saw this. All the hospital data per day on people dying from respiratory diseases per age class is publicly available. You can just download it from the web. So per age class, you know when did the people enter the hospital, how long have they been sick, and when did they die. So this is just downloaded from the web.
Is this per hospital or per region? Or
We did it on, it's for different cities, and we only did it for Manaus. If we had more time, I would love to do this for more cities, but unfortunately my student is moving on.
But the data is per hospital or?
I think it's per city.
It's per city.
Per city, okay, yeah.
And so what I also find remarkable is that actually the SARI numbers are almost the same as
Yeah.
the excess death.
Yeah.
So nobody died outside the hospital from COVID. I mean, here in the Netherlands, there were many people that actually died outside the hospital from COVID.
Yeah, but so I think the excess deaths were underestimated.
Oh, okay.
That's sort of thing. Yeah.
Yeah.
Then people did all sorts of studies measuring whether people had antibodies to corona. All that data is publicly available. Let's look here. March 2020, these are antibody levels specific for corona. And then these horizontal lines are sort of thresholds, and that's the agreed for today that if you're above this 1.4, then you have immunity to corona. So early 2020, nobody had immunity to corona. Natural, because the virus had not arrived yet. Then during April, May, June, you see that so every dot is a measurement here. You test seropositivity in individuals. You see that a lot of people become positive for antibodies to corona. So they have seen the virus. That's the zero prevalence. And then the next few months, you see this slowly declining, and people on average fall below the protective thresholds of the antibody levels. And then in November, December, you see it increasing again because the second wave appears. All that data, so the number of samples, the level of the antibody, all available online. Beautiful. I wish Holland would do something like this.
Is there a change in the number of tests?
Yeah. This is data on the fatality. How many people are, what fraction of people are dying from the disease over the different age categories. And then here, so you have age categories on a linear scale. And then here on a logarithmic scale, the percentage of people dying when they have the disease. So if you are 80 plus, there's about 10% probability of dying from the disease. And if you're young, there is about 0.01% of dying in the disease. Also available in studies. We know the population structure in Manaus, and it's special because 80% of the people are younger than 50 years. It's a community of people, lots of a working community, people working in factories and things like that. And there is papers that for different cities sort of project the contact rates. So contact rates between age classes and other age classes. All that information is available. It is outstanding.
there was a research group working in Manaus on this, so detailed.
So that was all done by independent people. So these were immunologists and epidemiologists doing antibody tests. This comes from a paper that tries to project these contact matrices for different cities in the world. It's a paper that all the epidemiologists use. And I think this is just from population census.
So this last one, so the PREM method, it's already started before the.
Yeah.
Okay.
Yeah. And here this too. This is the population structure just before the pandemic came. Yeah. Okay. From these measurements, we calculate the fraction of people that are protected by just taking the fraction of blue dots over all other dots. And then you get this curve, and that is your zero prevalence curve. In the beginning, about 50% of the people have antibodies. You see it declining, and then you see it rising again during the second wave. And in our model, we will say that the recovered people, the R class, they should be seropositive. They are in the protected antibody level. These people are immune. And if you wane, you fall out of this protective class. This was our pilot study. We take this new SIRW model. What is it? 5 differential equations, 7 parameters, and we bluntly fit it with least square fitting to the excess death data, and also to the zero prevalence data, and the model fits the data fine. What do we get out? Reinfected individuals hardly die, but lots of people get reinfected. So the death rate of people that get the second strain after having seen the first strain is 100-fold lower than the death rate of people seeing one of these strains for the first time. We also tried, we have this new model with the W and the I2 classes, I2 prime classes. We also tried normal SIRS-like models, and the standard SIRS models fit the death data fine, but never fit the zero prevalence data well, because an SIRS model needs a large second wave to explain all these deaths during the second wave. And our new model can apparently deal with a smaller second wave in terms of zero prevalence and still have higher deaths. But
what is the zero prevalence exactly?
that's the
You showed this here.
that's this curve. So from the antibody data,
Yeah.
you test what fraction of people is positive.
Because the curve in the next slide looks very different.
Yeah, this is earlier work, and this, I'm mixing up two versions. Yeah. But since Brazil is such a beautiful country, we have age-stratified death data, we have age-stratified zero prevalence data, we have age-stratified contact rates. It's a bit stupid to just fit this with 5 ODEs. There's much more information there, much more detailed information there. So the next step was to really make a model where you have age classes, I, and then we also improve things like saying, here I have my susceptibles in a particular age category, they can get infected, and then we model the infected stage not with a single ODE such that you have an exponentially distributed time spent in your infected stage, but we do this with what is called an airline distributed space. So you say I'm infected individual day 1, day 2, day 3, and then you get a more gamma distributed live residence time in the infected category. That's not so important, it's the same number of parameters, and you play a bit with how many of these subcategories do I make. This is your primary infection, you get recovered individuals, they wane, they can get reinfected, But also, if you have remaining susceptibles, if the second strain comes, they get a primary infection. And so with the same sort of parameters, beta 1, beta 2, beta 2 prime.
And you keep these the same for all the age classes, except
Yeah.
except the death rates.
Yes. Yeah, so the infection rates are the same for all age classes, and the death rates are different. Remember, we had this graph, death, age category, death rate, this log linear relationship. We knew that, so we knew that we had to do different death rates.
But these aren't all ODEs anymore.
They're still all ODEs.
If you say that this recovery time is some gamma distribution.
Yeah, but that is just a trick. You go from susceptible to infected day 1, from infected day 1 to infected day 2, from infected day 2 to infected day 3. And if you do enough classes, then it becomes a gamma distribution. So you just chain a few ODEs, and then you get a different distribution.
But between all these boxes is an ODE,
Yeah.
and then if you just zoom out, then you get.
Yeah, if you sum the infected, then the residence time in the infected subclass is gamma distributed.
Some exponential distributions.
Yeah.
There's some models where in between the S and the I stays, there's something there.
Yes.
Exposed, so effective, but not sick.
Yeah.
So that's, I forgot that was important because
Yeah.
it took a number of days between
Yeah.
being affected and affecting others and really getting sick.
Yeah.
Is that relevant here?
Well, we decided not to do it, just to keep it a little bit simple, but indeed, you could say from susceptible, you first go to exposed, and then you go to infected and infected and infected. But since exposed individuals also transmit the virus in corona, you could also treat the first infected class as an exposed class. That's why we sort of thought, let's simplify this way. Please.
Oh, can I have a question?
Sure.
So now it's become a very big system, but can I still using the same system with 5 ODE, but the parameters I sample from some distribution?
Yes.
If you said you have gamma distribution, I sample beta from gamma distribution.
Yeah.
Do you think they produce the same result?
That is what we're going to do.
Okay.
So indeed, we now have this system with many differential equations. On the next slide, I will show we still have only 11 parameters. But we are now going to fit this in a more fancy way. We're going to fit this with Markov chain Monte Carlo methods. So what you do, all parameters get a sort of prior, and then you sample over from these a priori distributions, you run change of fitting the model, several chains, and then you sort of get a composite of parameter values that fit the data well. That's the sort of state of the art of fitting these models. I can make a little joke here. I did this first project with the student. Then I talked to the epidemiologist, Michiel van Boven. He said, beautiful results, but if you want to publish this, you have to do an MCMC model because the world will not accept a simple paper like doing just 5 ODEs. So we did this just to be able to publish this, but I'll show that we get some very nice results out of it. Yeah, so this is the STAN environment. It's a steep learning curve. That's why we made use of Chris van Dorp, who is an expert on STAN. But once you know how to do this, it's really beautiful. Time consuming, but beautiful. Okay. Yeah, now we can
Time consuming in the sense of setting it up or doing the computations after
Both,
you set
both.
it up? Both. Okay.
Yeah, so the student took months to really learn the language. It's a language. And you can call that language from R, but basically you have to define all your model and distributions in a sort of statistical language. It's
And then the simulation itself also takes.
some simulations 2 weeks. Yeah. And if you want to do STAN, so there is this website, and there is tons of examples on all sorts of problems. So if you want to do an epidemiological problem, you just download an example of somebody and then you sort of tailor it to your own needs. That's the way to learn the system. Otherwise,
Only for epidemiology.
no, there's also all sort of other models. Yeah. Yeah.
Oh, there's no mic.
Yeah.
Thanks.
Okay, our core business. How many parameters are we estimating? At 11. What are we estimating? The length of the infectious period. Well, remember, and gamma is this rate at which you leave the infectious period. So 1 over gamma is a parameter that we estimate. But we sort of know that the infectious period in corona is a week or so. So we have a good prior for this parameter. We are estimating 3 infection rates. The infection rate by the first strain, primary infection by the second strain, and reinfection by the second strain. So that's three parameters that we don't have good estimates for, only that beta 2 should be larger than beta 1. We're estimating the waning time. There is some prior for that because we know how fast antibodies decay. So you get an idea on how long would it take for them to decay below the protective level. And then the death rates, and these are very important. I already showed this curve, there's data on that, but we didn't use it. We said these death rates can be described by just a linear line with age category, linear, and death rate or fatality rate, I should say, on a logarithmic scale. So we define the death rate by an intercept and a slope of that line. And then that is
Like a parallel.
Hmm?
Some parallel with the age or something.
Yeah, so here's age.
It's the explanation one, I'm sorry. I've got
Yeah.
this on my phone, so I can't really-
Yeah, so age is linear, and then the death rate is a power of that. We do that for the first strain, because there's a death rate associated with the first strain. We do that for the second strain, so then we have 4 parameters, 2 intercepts, 2 slopes. And for the reinfections, we say we take the death rate of the second strain, but we shift we shift it vertically downwards. So we have a set. How do I
So
do
we
those?
start twice, yeah.
Okay.
You have to see.
Go in view, in view.
No, I don't think so.
Full screen.
What?
Full screen.
Yeah, but then also here.
Zoom ratio. Fit to window.
Thank you.
That's perfect.
Advanced.
So I should keep a safe distance to the screen. For the death rates during reinfections, we just shift this line vertically down. How much protection against death is there if you are reinfected? But that's just one extra parameter, the scalar for the reduction of the death rate in reinfected individuals. Then we have to estimate the introduction moment. When did the first strain arrive? And how many individuals was this? When did the second strain arrive? But this is basically very well known. We know when these strains evolved and when they arrived. And then if we can set the dates, and then we sort of estimate how many people did it start with, or we estimate at what date did a single individual start the pandemic. So that is the 11 parameters.
Wait, can I ask you?
Sure.
One thing about the first one? Because you said something about you actually make different categories of infected individuals, and so you have an airline distribution. So what is exactly your infectious period 1 over gamma? Is that the mean of that distribution, or what's or is it the transition for every box between every box? What is it?
Let me say it somewhat differently. If you would do the ODE, then gamma would be the rate leaving the infectious period.
Yeah.
Then if you make n subcategories, then you do n times gamma.
Okay.
Okay, now the model predicts the people dying from corona. That's D1 times the infected ones, D2 times the infected twos, and D2 prime, I1 prime. So the model predicts something. There is an observation how many people died this day. And this is all stochastic, so that we take a Poisson distribution to match the data with the prediction of the model. And the same we do for the zero prevalence. The model predicts R1 plus R2 over N. That's the fraction of people with having high antibodies. We know at every day how many samples were taken. So we use a binomial to say how many positive people do you expect on that day, and that is what you fit by the model. And that is all small letters there, per age and per day.
Contact matrix remains
Constant. Contact matrix remains constant, and also the age distribution remains constant. And that is the contact matrix will change because
distancing and so on.
Bolsonaro didn't do any lockdowns, but people did lockdowns themselves. Yeah.
So every state had autonomy to declare lockdowns.
Yeah.
Then what happened, the states who support Bolsonaro didn't do lockdowns. They stated who didn't support did lockdowns, and some drug dealers did lockdowns. They thought that was they declare. They control the area, and they say if you go out, you get shoot. So there was lockdown.
Yeah, so we decided to keep this, and it would also be very difficult to do this. Otherwise, you need lots of data to know the change in the contact rates between age categories. Okay. Now I can show results because everything is clear. So this is the result of fitting this model. Look at the heavy lines, that's the fit of the model, and then we have all the credibility intervals around it. It's split up by age category, so 0, 10, 70 plus. This is the death data, and first wave and second wave. And then you see here, for instance, in the higher age classes, the model fits the death data very well. It looks as if the model doesn't fit the death data in the young age classes very well, because this heavy line is by no means close to the heavy data, but there is a lot of zeros on the horizontal axis. So actually, it's fitting that data very well. There's a lot of zeros that you don't see. Right? This median here is nicely the median of the two. So there's a lot of, there's a lot of data points on the horizontal axis, people not dying. And you don't see that. Here you can see it a little. There's no data points. On those days, there's more than 0 people dying.
It's also like, you know, you're talking about one individual dying.
Yeah. That's why it's good to do this Poisson type approach.
Sorry, tense. Yeah, I know.
Okay, so that is the death data. But the model also describes the zero prevalence data very well. Also, again, per age category. Here, for instance, the 30-40 age category, you nicely describe the zero prevalence in the first and in the second wave. That's good. If we now do the same thing with a SIRS-like model by making the reinfection rate the same as the primary infection rate for the second strain and making the fatality the same, then the death rate are well described by an SIRS-like model, but the zero prevalence data is not well described. We also saw that in this sort of pilot. SIRS models need a large second wave to explain all these deaths. So that's why we now say, yes, our model is really an improvement over classical SIRS models. It makes sense to define a new category, waned people. They are not the same as susceptible people. That is, for me, the biological take-home message, or the immunological take-home message. Okay.
Wait.
Yeah, please.
Sorry. You've now taken beta 2 prime equal to beta 2, Do you refit the data again?
Yeah.
You refit the data again?
Yeah.
But then it's, you're still having this, waned class. Oh, that now becomes, of course, equivalent to
Yes.
susceptible.
Yeah. And also the death rate we make the same.
But it's not the same as the, still, it's not
Well,
the same as above because you have,
true.
you don't have the beta two prime in,
Yes.
in that top graph, yeah.
But what people, so this is a sort of summary of the literature. People have either done this, that they allow recovereds to be reinfected, or they allowed recovereds to wane. People never did the two together. And so we sort of do a general SI. That's why I call it SIRS light model.
How many parameters do you fit in the classic SIRS model? I mean, so
You mean without age categories?
so for the first data you show
Oh.
us that we have 11 parameters, and then you say, okay, in the classical
Yes.
way, the fit is worse. How many?
That's a good question. You could indeed say we lose beta 2 prime as a parameter, so that's one parameter less. And having a fatality rate, the fatality rate is 2 parameters. Yes.
So
We lose 3 parameters.
2 parameters less.
Yes, 3.
3 less.
Intercept and slope and beta.
So that means that you just a priori expect 11 parameters to be better than 8, independent of whether or not your model makes sense. If I'm being very critical.
Yes, that's okay.
Yeah.
You're completely correct. And it's good that you point this out because I never realized this. Nevertheless, I see a sort of systematic thing. The SIRS-like model cannot explain higher deaths in the second wave with a smaller wave.
I believe this
That-
model makes sense.
Yeah,
That's
yeah.
not
No,
the point.
but it's a good point.
Yeah.
There's a parameter difference there. Yeah.
Why do you fix what's up there on all the other left? The beta 2 prime equals beta 2 and the fatality rates are also the same. So why fix that? Because you can still do the MCMC fitting for that series-like model, even if you leave those parameters.
Yeah, but it is sort of the same. See? Let's go back again. If I make beta 2 prime the same as beta 2, then the waned class is identical to the susceptible class. So the waned class doesn't have any meaning anymore. And if I make the death rate of the reinfected the same as the death rate of the secondary infected with the second strain, then again, so these two blue new things in our model collapse to this becomes that and W1 becomes S if we do that.
But you're showing the graph for the not for the new model, but for the series-like model.
Yeah, but
So that have some.
yeah.
Except for this beta two.
For the beta 2. Look, if you go back to S, if I make W1 equal to S, then you just go back to S here. And here you have your infection and the beta 2, where am I? Oh yeah, I don't want order death rates for the reinfected class because in this model being reinfected is just a separate category. There's only one I2 class in the first model. I cannot allow for 2 I2 classes in the first model. So I make the death rates of these 3 populations the same, and I make W1 the same as S, and then I say it boils down to a model like that. There is more variance, I agree.
So people not only die from the second variant, but also from the first. So you can also go from I1 to 1, so recovered or removed. I thought that these 2 different infection or the fatality rates were for dying while being infected with the first strain versus dying while being infected with the second strain. But now
You're right.
you-
I think there's a typo here.
Here, just-
IFR2 prime equals IFR2.
Okay.
It's a typo. Yes, you're completely right. Thank you.
Now,
Yeah.
how the beta true prime compares to the beta true? Could you say the beginning would be much bigger or for the second?
Well, actually the parameter is fitted. So the model tells me what beta 2 it prefers.
Yeah, so which one the model prefer?
I think the answer is on the next slide. So,
Okay.
so in this model fits the data less well than the previous one. It has more parameters. That's your contribution over there. But there is also this qualitative difference. So we prefer the previous model. And then the parameter estimates of the previous model will be on the next slide. Yeah.
But so your model now over predicts the zero prevalence,
Yes.
so higher numbers have the disease.
The model needs higher numbers having the disease to explain all these deaths. The
Model needs higher numbers of individuals having the disease, which is kind of counterintuitive to me because you actually increase the death rate.
Yeah, but the death rate is fitted to the data. So this model, the SIRS model, fits the same death rate as the previous model.
Sure, but
Because this fit is sort of equal. And it can only achieve that death rate by having a higher wave, more people infected.
Or having no treatment.
Yeah, but that is, I'm still trying to say that would be the same, because we don't know, the death rate is determined by how deadly is the virus and how good is the treatment.
Yeah.
That's a composite parameter.
Ah, yeah, so then you would be, okay,
Yeah.
okay.
Can I ask you a question?
Yeah, please.
Again, about defeating the fact that you have like more parameters here versus the previous, less parameters here than the previous model. In the previous model, what if you had reduced one parameter and tried to see if one has more impact than the other? For example, you have beta 2 and beta 2 prime, and you have the death rate for so
Yeah.
can you go back? I don't remember the names
Yes.
of those.
But maybe you should go, let me first give you the results. And then you can appreciate that
Okay.
it doesn't make much sense to
Now.
let one of these. And
one versus the other.
perfectly happy to discuss this, but let's first deal with the next 2 or 3 slides. So bear with me for a while and agree that our first model describes the data reasonably. And now we can ask, how is the first model describing the data? What parameters is it fitting? That is, I think, what you were asking. Well, the first model says beta 1 is about 0.16. Beta 2 is about 0.34. So the second strain is more infectious, twice as infectious, more or less. That makes a lot of sense because the second strain was facing a population with partial immunity. But the model also says beta 2 prime, the probability of getting infected with the second strain, if you have seen the first strain already, is 70% lower than beta 2. So immunity gives you 70% protection against reinfection with the second strain. That is how you would phrase it. I don't like percentage, but it goes down by 70% from 0.34 to 0.1. So immunity is doing something. And lots of people said there is no herd immunity there. There's so many people dying. Immunity reduced the infection rate of people that had seen the first virus. But this is just peanuts. Because if we look at the estimated fatality rates, then here in blue, you see what we estimate for the first strain. Age categories, linear scale. Fatality rate on the vertical axis on a log scale. So the blue line is what we estimate, remember, slope and intercept. And the orange line is what we estimate for the second strain. So the second strain is more deadly. The orange line is above the blue line. but the slope is not the same. The second strain is also relatively more deadly for young people. The death rate of young people increases more than the death rate of old people. Yeah. Now the question is, how about beta 2? Death rate prime. Remember that we were shifting the death rate of the second strain vertically downwards to describe the death rate of the second strain. And that line goes down 100-fold. So if you have seen the first strain and you get the second strain, your probability of ending up in the hospital is 100-fold lower. And now I'm happy as an immunologist. The immune system is reducing your risk of dying by a factor 100. And that's a huge effect. So that is, I think, the main thing that the immune system is doing here. It's protecting us from death. It's not hardly protecting us from reinfection, because that only went down by 70%. But there's this 100-fold reduction in the probability of dying from the disease. So that is the main take-home message. Here's a little bit of confirmation that what we are doing is sort of okay. Here's this plot that I just showed. Remember that I showed this data in the beginning. And we didn't use that data. If you now compare, how do we compare with the death rates in the young age category and in the high age category? Then apparently our model is capable of estimating published death rate from the data. And there is here another study estimating death rates for this infection. And again, you see that the model sort of agrees with that. People have estimated that reinfected people have about 90% reduction in the death rate if they are infected with the second strain. Well, we say it's 99%, 100-fold, but at least it's in the same order of magnitude. So this gives me some trust that the parameters that we are estimating are reasonable. They match with other data that were retrieved, with other estimates that were retrieved in a different manner.
I have a question about the parameters being reasonable in the sense that your MCMC method gives this kind of distributions about how value parameters are fitted. So this gives you 11 very sharply fit distributions, or
yeah. So let's go back.
So you showed it for 3.
Yeah. So for beta, that's these distributions.
These are all very sharp. Yeah.
And this is 100 different lines. And the blue line is also 100 different lines. And here you also see 100 different lines. So there's more uncertainty in estimating how much reduction or do you get.
Yeah.
But these death rates are within reasonable bounds.
The same for the other parameters. They all have very small uncertainties.
Yeah.
Okay.
A reasonably small uncertainty. Yeah.
We were down to this more uncertain than the other parameters. I mean, the reduction in the death rate for the second infection.
So the death rate with primary infection with the second strain is, say, well defined with small bounds. If you then ask, how can I estimate the protection if you have seen the first strain before, then you see that so this is 100-fold. It goes from 10-fold, 100-fold to 1,000-fold, more or less. Yeah.
I'm just guessing, maybe related to the fact that the reinfection slope that not necessarily has the same slope, and because you only change the intercept, not the slope.
Yeah.
So if you maybe add a 12, parameter, maybe it would be.
Yeah. Well, here we could have played a little, because is this slope significantly different from that slope? Maybe all the slopes would have been the same. That is, we could have played a bit more there, reducing the number of parameters. Yeah.
Yeah.
And indeed, we could have used 2 parameters to estimate the reduction in death rate, and then the slope of these bottom lines could have been different from the slope of the top line. Yeah.
And also, what we're talking about these difference in slopes and intercept, is there some effect from the fact that in the first wave, mainly elderly people died So in the second wave, you see less elderly and more young people because there are just more young people and less elderly people remaining, or is this not a big effect?
It is an effect, and I have a slide answering that halfway, and then after my conclusion slide, I have a slide answering that 100%. So
Okay, great.
maybe,
I'll wait.
yeah. This we do. So here's this slide answering that halfway.
In the previous slide, so do you you now basically show the data comparison with model fit? Do you just look at the first the curve for the first wave? The green?
Yeah, this is all the third wave.
Yeah.
Because data is not available for the second wave.
Okay. Okay.
Yeah. Yeah, so the inference is if we can just estimate parameters of the third wave, then we sort of trust the model also on the second wave. So this is getting close to your question. It's a sort of busy slide. Here we have all age categories. The top line is the number of infected individuals in that age category. Then the solid line is the two primary infections in that age category. And the dashed line is the reinfections in that age category. And the only thing that I would like to point out is that in young people, there's more reinfections than primary infections of the second wave. Young people were massively infected in the first wave. They do get reinfected, so almost infections in the second wave are reinfections. Older people, it's the other way around, the solid line is above the dashed line. There were quite some susceptibles left in the older people. They were probably more careful, not contracting the disease. So they experience more primary infections with the second wave than reinfections. And hence they are dying because the death rate from primary infections of the second wave was really high. So the narrative that comes out of this is that in the second wave, people were hardly protected against reinfections. So lots of people got reinfected and the majority was young people. These were infecting the remaining susceptibles in the older age categories, and then these people were dying. That's why we get a lot of deaths in the second wave. There's a massive infection going on because there is so little protection against reinfection. Two or three more slides, and then maybe the end slide for you. If we trust our model, we can go back to the title of the talk, because I didn't come back to that yet. How herd immunity mitigated the second wave of COVID in Manaus. We can do a sort of, it's called a counterfactual, a what-if scenario. What if I had blocked the second strain by forcing lockdowns for half a year? Or what if, sorry, I say it wrong, sorry. What if I had blocked the first strain? Or what if the first strain had not happened? We can do that in our model. So here in red, you see the data, cumulative deaths over the whole period. In black, you see how we describe the data with the model. And then just look at the light blue line. Suppose we completely block the first wave by reducing its infection rate below R0 equals 1. Then you don't have deaths in the first period because there is no first wave. But you have a lot more deaths in the second wave because people don't have partial immunity. You get twofold more deaths, or 12,000 extra deaths. So the first wave with all these mass graves was good news. It protected a lot of people from dying. You could also say the immunity that was built up by the first wave protected a lot of people from dying. So nobody should say anymore that there is no herd immunity after the first wave. There's a lot of people dying, but if there were no herd immunity, there would be twofold more people dying. So the immune system is doing an excellent job there, I would say. It's preventing a lot of deaths.
But there would also have not been a second wave if the first wave had been there.
No, so this is
So it's like, because you know, the second wave is a more infective
Yes. Yeah.
disease, so, yeah.
Although you never know. At
No,
least
no,
I can say the first wave was good news because it was lethal and it immunized a lot of people. It also killed a lot of people, but these people would have been killed by a second wave anyway, and then even more people would have died from this disease.
It was a great thing around the uncertainty confidence
Of this 50% thing,
no, the gray band.
oh, that's just remember it's all this stochastic fitting. We have posterior distributions, and we sample from the posterior distributions to do sort of certainty around the predictions. It's written in other slides. I don't know by heart. No, I'm going the wrong way around. Sorry.
It's the uncertainty around the.
Here, dark shaded areas are 95% credible intervals. Light shaded areas are Bayesian samples from the posterior distribution, something like that. It's two
But they're
ways.
not for the counterfactuals. They're for the ones.
Yeah, that's for the. Yeah, but the counterfactual was just running the model once for this parameter being reduced by 50%. Yeah, we didn't do. Is that? I think, yeah, it's a single line. Yeah. Almost done. You can split this up by age category. And then you see that it's even worse because the death rate would have increased most in the youngest group. So if the first wave had not been there, there would have been more children dying, relatively speaking, than the increase in death rates of the older groups.
That might be.
Shall I skip this slide? Yeah, we're sort of running out of time, right? Yeah, let's skip this slide. This one.
We continue to.
Okay.
No, but the problem.
Let me go back.
Isn't that partly related to how you actually model the reduction in death rates? Because what you saw is that this IFR2 was had a higher intercept than IFR1. And I was wondering actually if that higher intercept is due to the fact that that IFR2 prime is just a factor lower. If you had decoupled the two and introduced a separate intercept for the IFR2 prime, would you have had a higher intercept for the IFR2? If you understand what
I understand what you say. It's a good question, and I don't know. Yeah.
Because somehow, it's like you have to fit two things, and it might.
Yeah, we fitted a lower slope for the second strain.
Yeah. And that might be due to the fact that you actually pulled something down with the IFR2 prime.
Yeah. Yeah, so the protection could have been age dependent.
Yeah.
Yeah. Yeah. That's a good point. Well, this is less important, but it's also the last slide before the conclusions. We did look at mobility data to know a little bit more about these contexts. And there is Google mobility data and people in traffic and things like that, people going to work. And you see that during the first wave, people stayed more at home. There was a 50% reduction in the mobility, and that we didn't model, we ignored it. But just before the second wave, there was a steep increase in the mobility due to schools opening, Christmas was coming up, and there were elections. And several people have blamed this increase in the mobility as the cause of the second wave. People were mixing more, so you get a big second wave.
Which country was the borrowed one?
Data
Data for a specific country or?
This is Manaus.
Is it still Manaus?
Yeah, still Manaus. So again, you can play, what if I would have reduced the mobility in the second wave? Prior to the second wave, what would the second wave have looked like? And that is sort of shown here. If you would have prevented this increase in mobility, you would have sort of broadened the second wave. But the area under the curve is not so different. So the number of deaths during the second wave is not terribly affected. But at least you can now address the question, did the second wave result from this increase in mobility? Yes?
Oh, sorry, I missed the connection, the mobility in your model, like a couple of lines.
Okay, I didn't say. So what you can do, so there's mobility data from Google, and we here sort of 0 means mobility level 1. And what you can do is multiply, and you can fit that data with this black line, a spline function, and you can just multiply your infection rate with the mobility, because if the mobility goes up, people make more contacts, and then the infection goes up. So we multiply the infection rate with this mobility when we do this. And then we can also play with the mobility. We can say, what if we reduce the mobility by 75%, 50%, that's the lines here. What effect would that have on the second wave?
And is it on this slide now, or in the previous model, did you also include mobility?
No, the models were all fitted without mobility. Partly because it was extremely time consuming to include mobility, and also partly because this is people sitting in trains, people sitting in, so it's not clear that for all age categories, this is the best measure of the mobility. So maybe you're just introducing more noise in your whole fitting procedure than adding true data. So we decided it's too complicated, we leave it out. But then you can still do a sort of, you can use it for the counterfactual to play a little bit.
Would this be similar to just an overall rescaling of the contact matrix, like you might see?
Yes, yes.
I remember in that this delaying and widening of the curve was something that people wanted to do in technology because that would impact the hospitals less.
Yes.
And then it would affect the death rate, and that would probably also affect your conclusion that it's
So indeed,
the area under the curve will be smaller if you look at that.
True. Yeah. So it indeed shows that if you do lockdowns, if you reduce mobility, then you flatten the curve. That was the word always. We want to flatten the curve. That works. You indeed flatten the curve. Okay.
Like they would avoid the collapse, because what was important is in the news, the second wave there was a collapse of the system. And the first there was like a saturation, but not collapse.
Okay. But there were indeed more deaths. There's twofold more deaths. Yeah. This is conclusion slide. I only want to discuss this, and the other things you have to read yourself if for some time. We started with SIRS models. We made a SIRW model, WANED, but I think we should go to an SIRP model. You go to protected. You never go back to susceptible. If you've seen the virus for the first time, you have some sort of immunity that is protecting you against it's protecting you against death. Maybe not against reinfection, but it's protecting you against death. And seeing this, you can also think of influenza. We get reinfected by influenza, but thanks to our previous immunity, we typically don't get very severely ill. You get severely ill from influenza if you see the virus for the first time, or if the virus has changed so much that it looks like a completely new virus. So maybe we should sort of switch thinking about the immune system as that it's protecting you, that it's not providing sterilizing immunity. You just get reinfected again. We get reinfected maybe all the time, but we don't become sick anymore. That is what the immune system is doing for us, at least. That is what this setting of the data say. Yeah, so malaria is the same. Well, and the seasonal coronaviruses, we all get reinfected with seasonal corona, but nobody ends up in the hospital because we have seen these viruses so often. Do you want to see your slide? It's similar to the one that I showed, but more complicated. The top line is the total number of individuals in an age category. And indeed, you see in the elderly category, the top line going down a little bit because these people are dying. The dash dotted line is recovered plus waned. So people that have seen the virus and survived. And then you see in the youngest age category that recovered plus waned is very close to the total. So almost everybody saw the virus. And in the older categories, recovered plus waned is just half of the total. Then in the second wave, recovered plus waned goes down 45% more or less. All these young kids get reinfected. And in the older categories, this is much less because these people they get less infected, but because they get primary infections rather than secondary infections, you still have the highest death rates in the oldest categories. But I thought this slide was a little bit too full.
Thanks a lot.
Cesar.
Great job. A question about because you mentioned the mixing matrix, but where did it exactly show? It showed up in your age-dependent model, I guess. But how did you incorporate it there?
There is a consortium of epidemiologists that have estimated mixing matrices for different cities, and then they also there is a paper and some sort of algorithm that from the population structure in a city, you can predict the mixing matrix for that city. And that is what everybody uses.
But you introduce it in your dynamic model as a multiplicative factor of data.
Yes.
Okay.
But when age categories meet, we have a weight for how often do I meet that age category. And then the betas are, as you already agreed, they are the same, they are uniform.
Yeah.
But how many people, 40-year-old individual, how many babies does he or she need, how many 80-year-olds this person needs? That's the mixing matrix. Please.
Nice talk, thanks so much. Like, I understand your immunology, so most interpretation you give it towards immunology, but most of the data is a populational level, so you cannot, apart from the seropositive, like the test, they are not related to direct measurements on immunology. So then, in your parameters, which factors you think are co-founded, like both by your interpretation in terms of immunology and both by what was reported, at least in the news, that was lack of treatment. So which parameters could have the same root in what you fit?
Can you say it again?
Elaborate.
Yeah.
Like you get 11 parameters that you fit, and of course you can, it's very nice in mathematics, really well made work, but some parameters are on populational dynamics. And of course, you come for immunological arguments. And what you see in the news was argument that was straight on lack of treatment, or which parameters of your model could be also attributed to the lack of treatment.
Yes, well, I learned something from you today. If I say the second strain was more deadly, there's at least some feedback there. If the second strain is a little bit more deadly, the hospitals are more overloaded, making treatment worse, making the second strain even more deadly. So if we say the second strain was twofold more deadly, that is not just the property of the second strain, it's also exactly what you say, the system was more overloaded during the second wave. And that's an important thing. Yeah.
But it is important, but your model capture everything. So that's what my question now with which parameters would capture these, because you fit the data much better than the normal models. So that's
it's the death rate.
It's the death rate. Yeah. So the death rates are related to, we indeed played with that. We even played with density dependent death rates. The more people are infected, the worse the care. And so you could say the death rate depends on the number of people in the hospital.
Yeah.
We played with that, but we dropped it because at some
Yes,
point you have to curtail your work, but that would be something like this. Yeah.
What about, because here the bad impact is the death, right? There are a certain number of people who die. But what about long COVID? That seems to be maybe a little bit different, where maybe if you have already a first infection and second infection, that the symptoms of long COVID can get worse. I mean, I don't know if it is well studied, but I've seen some studies about impact of vaccination on long COVID. And the impact was negative in the sense that it was positive for the death rate, but it was negative for the symptoms of long COVID. Have you looked into this?
No, so the thing about vaccination and long COVID I didn't know about. And I was expecting when I talk to people about long COVID, and then typically they tell me vaccination or reinfection protects you against long COVID. The probability of long COVID is the highest in the first infection. But I'm not an expert on this. It could very well be that you know more about this than I do.
Because I was thinking in this case where you have like it's kind of it may be kind of the opposite in the sense that the more you get infected, the more overreactive your immune system can be, and then it can create more. If you end up having symptoms of COVID, it can create worse than symptoms. But I don't know.
Yeah, but then a lot of these reinfections in the second wave, there are probably people not even noticing that they were reinfected. Most of the reinfections are very mild, but maybe some of them are more severe, and I don't know. So typically reinfections are much more mild than primary infections.
Because that's not a populational study, then it's more a study immunology response of people that are COVID. It's not a population level thing, it's more unique to the statistic.
And with the population of people who have long COVID, so among the people who have long COVID, what was the impact of having one time or multiple time infections?
I don't know.
And the immunological response of the body.
Following up on Panando's question, is it possible to like include hospitalization or something in this kind of model to like segregate the effect of what immunological effect and scarcity?
Yes. So one thing that we could have done is to say you're fully protected, you're mildly protected, maybe you're still protected against death. So we could have defined classes of antibody levels. But then again, at some point you should make your model a lot more complex.
Yeah, I have more feedback than a question, because I think it was very nice work, but probably, I don't know how you choose Manaus, but probably because you also listened in the news.
Yeah, exactly.
But in every state, there was some states with one wave, some states with two waves, but Manaus was the state that had collapse. So that the effect of the death is also due to the lack of treatment.
Yeah.
But because the data is very nice, feedback, you could get data from other states that had two waves and no reported collapse.
Yes.
And then your argument is truly only, let's say, for immune system.
Yeah, I would love to continue this by doing other cities, and then because the strain is the same in other cities, but the population structure will be different. Maybe the death rates are different due to different hospitalization levels.
Yeah.
It would be beautiful to extend this to more cities, but then I need more students.
Okay, I think we could continue the discussion over lunch.
Yeah, thank you.